Hello everyone, welcome to this stream. And today it's been a little bit of a while since our last stream, but I was working hard on something really cool and that I would like to show off today. As you remember, we were working on the Twang game. So there's this, it's the wrong one. So this is, you remember this game where you have one linear LED strip, and then you have a game of like a dungeon that you're going through with obstacles and whatnot. And then you have a controller with a joystick so that you can move the dot that is your character around and whatnot. So I started with that early in the year. This used to be a motivator to look at how to implement this or port this game that is originally for Arduino to the Icebreaker. So looking into that, then we realized, well, we need an SoC or a microcontroller on the Icebreaker as well as some peripheral hardware. So I sent out a tweet to the community asking, what is... So let me rewind one more step back, because I started doing this in Python, thinking about CircuitPython and MicroPython. But while doing the streams and implementing it at least on a PC, like as a simulation essentially, I realized that I should ask people what environments they prefer and how they would like to program a microcontroller, so that at least as a side effect, I have the right environments available to people as examples, so that if they want to implement similar things or other things on the Icebreaker, they can use the work that I've done for Twang as a starting point for the Icebreaker. So I sent out this tweet with a poll as well as a Mastodon toot, and people were pretty like even on the MicroPython and was it, I think MicroPython and C. I don't exactly remember what the results were, but essentially the main thing people really wanted is just give me C and make, and that's it. This is something I was expecting to a certain degree, but I was giving the option of Arduino also, but that like lost really badly compared to other options. We now, because I realized I have to do this, I had to see forever exactly. What I did now, because the second in line was, I think, MicroPython and as well as Rust. So the path that I had to take is actually to start implementing and getting the microcontroller to the Icebreaker. So as a side note, while I posted that poll and after the results were in, also Mithro, Tim Ansel, he commented on that, and he said, well, we have some microcontroller stuff for the FOMU, which is the same FPGA as on the Icebreaker, which is the ICE40 UP5K, and they have an SoC based on Litex. I will explain all of what is what in a minute. For makefiles. Arduino is the gateway for makefiles. I'm not sure I understand what that means. Anyways, so now it turned out a way bigger project than I expected. I thought I will just take the FOMU stuff and just port it over. But it turned out to FOMU being very specific and having a lot of features. The build machinery around this and Litex itself, which is quite a big, massive machine and complicated as hell because of it and because it's flexible. And because it is actually meant for really big FPGAs where you can run full Linux distributions on it, it was quite overwhelming to me, and it was a very steep learning curve. But thanks to Sean Cross, who was just an angel and patient with me and like trying to help as well as he could. And he did help a lot to get the example build script pared down to just the essentials, sort a few things. We figured out a few fixes to the way LiteX is managing things so that the whole build system became much simpler. So after essentially weeks of work, we'll not continuously, but we worked on that for a bit. We actually built an example that I think is fairly simple, fairly transparent and easy to use, and should give a very good stepping stone to start adding your own hardware to the SoC itself. So SoC in this case means system on chip, so it can be a CPU core with some peripherals, but in theory it could be just peripherals and some state machine that is running it all. So LiteX is a little bit vague about this, even though it is meant to generate a CPU as part of the system. But anyways, so I will try to show you. Oh, thank you for the subscription. Thank you, Ultiman. Okay, so let's see this desk. No, this is the wrong desktop. Huh, funny. Why is my face so big? Let's fix that here. Yeah, I had to mess around with my video settings. So yeah, if you might know, this is the icebreaker. This is what we will be programming, and essentially today. And here's an LED strip for the twang. But yeah, so we will be running everything on this icebreaker here. And the example code that we will be using is here, which is on the Icebreaker FPGA organization, and then Icebreaker LiteX examples. So I am still curious what is the best way of showing you the structure of it. So I think we just start from the top what the repository actually consists of. So there are two layers to all this. There is the FPGA itself, then you have the bit stream, which we will be programming on it. And the second step on top of that, is programming the SoC that runs on the FPGA. So unlike a microcontroller where you just have the fixed core and the fixed peripherals attached to it, and memory and flash and RAM, in this case, we are actually configuring the FPGA to behave like a CPU. And so you have the core and you have some peripherals that you design into it. So the core thing is the SoC here, which is this here. And it essentially is just one Python script that pulls in a bunch of stuff. So let me just open this. Oh, I didn't open Sublime. Interesting. Okay, so this is the script. I hope that is somewhat readable. So one interesting thing about how this is built is this. The Python script automatically pulls in dependencies. So it's really a problem with Python and the build systems, how they work, that you have to usually create a virtual environment and whatnot. This script actually takes care of it so that you don't have to think about this. So this is the LX buildenv, and then we are using a bunch of LiteX stuff as well as Mygen. So this is also an interesting thing. If you are a little bit more familiar with how the HDL environment currently looks like, it is we currently, for the open source FPGA development, we use either Verilog and directly Yosys and iStorm or Project Trellis and NextPNR to generate your bit streams. Or something that is very popular is using a Python-based it's a DSL in a sense, but it's more written in Python generator for logic. So there's MyGen and NMyGen, which NMyGen is the new MyGen, which is the next generation developed by White Quark, and she is making a lot of improvements on top of MyGen, which is the predecessor to it, and essentially lessons learned, how to do things better. And so a lot of people, when you ask them, like, what should I learn? Should I learn Verilog? Should I learn MyGen or NMyGen? Usually, if you don't need to use LiteX, the answer would be NMyGen. Unfortunately, LiteX is not ported to NMyGen yet. And how this works is LiteX, like the core, the top-down thing would have to be written in NMyGen, and we would be able to use legacy MyGen stuff with like a compatibility layer, but we cannot do it vice versa. So it means because we are using LiteX to design the peripherals and plug in the CPU, we currently have to stick with MyGen and not move to the new, better, improved thing, NMyGen. But I hope this will happen sooner or later. Holzfrau, welcome. No, I don't think you missed much. I was just telling the history of what we are working on, and we are just starting to describe how the SoC is built. So, oh, interesting. That was missing there. So, the main build thing is this main script, and this essentially puts together the base SoC, takes a bunch of parameters, and puts together the SoC itself, and then sets some Yosys configuration parameters. And oh, welcome, Mike W. Meek, oh, that's Meek probably. Mike Walters, welcome. It took me a moment to parse that it's probably you. All right. Then after this SoC is built, the rest is basically a builder and a documentation generator. The cool thing about LiteX is also that it can not only generate the SoC, which we will get into further and further, but also it generates documentation of the SoC, which you will see here. Let me do some foreshadowing here. So you get documentation like this for a core, which says what registers there are. So this is so-called CSR, so it's configuration and status registers. And you get information about where they are in the address space, what bits they have, and additional text as a description. So LiteX can generate this documentation for you, which is nice. And this is what happens after the SoC itself is built and synthesized using Yosys. You can forego it. It's like there's some details where it's like how you run the scripts, and at the end it can program the bit stream to the icebreaker. Besides the documentation, it also generates the C headers for you, and it generates an SVD file. That should be SVD here. Yeah, there we go. So an SVD file, which can then be used by Rust to generate headers for Rust, or the way to interact with the registers in Rust. So this is quite powerful and makes it so much easier when you make changes to your hardware. It propagates to the documentation, as well as propagates to your C or Rust code so that you can access those registers fairly easily. Of course, drivers that are on top of this have to be aware of those changes, but you can definitely abstract the things a little bit. So if there's like address changes or bit width changes, it should, to a big degree, be compatible and not break things when you make those changes. Okay. So next step is how the SoC itself comes together. It uses MyGen platform definition of the FPGA itself to know where the pins are. So if we look in depth, so in depth it's a Git sub submodule, and this is loaded in there. Yes, so Sylvain is asking a very good question. Can you fix those addresses so that they don't move around? I think you can. There's definitely, you can override how the table looks like, I think. I saw that, especially here in memory map, I know that this is something you can do so that the SRAM, SPI flash, CSRs are not moving around. This is something you do to fix those addresses. I am pretty sure there's a way to do that for the CSRs themselves. But that's a good question. I don't exactly know how exactly to do that, but I'm pretty sure it is doable. But in essence, it's not necessary because the headers are being auto-generated. So you just recompile your stuff and you're good. So it shouldn't, this is why you generate those headers, so that you don't have to fix them to a specific position and rely on them being always at the same spot. So there's a thing, but I would assume that you can force that a peripheral is always at a certain address. Especially if you have something that you have to access from assembly or in a startup code, that might be very useful. Okay, so platform. We wanted to look at platform, and by now the Icebreaker is actually in the full upstream LiteX environment. So we have the platform, and the Icebreaker should be here. There we go. And this is a definition of the FPGA itself. Here you have all the definitions of the pins of the FPGA itself. This is pretty self-explanatory. User LEDs, which pin on the FPGA they are, and what I/O standard is being used. And you can have also groupings of I/O, which is a subsignal. So RX, TX for a serial interface. Same thing for SPI flash, or a SPI flash that is quad SPI, and so on and so forth. The clock pin is defined here. And then we have connectors, which we might see later how they are being added. So the breakoff PMOD, which is the head of the Icebreaker, so this guy here, this section on the top, it is electrically connected to the PMOD, so you don't have to break it off immediately. This is the breakoff PMOD, and we can essentially just add it to our platform by platform add extension, which you see here. You can just attach this, and then you can access and request those pins. So that is the FPGA side. So that's the layer on the very bottom. Then with that platform instantiated, we can we do some argument defaults. Let's not get too deep into that. So you can, in LiteX, you can even choose which CPU core to use. There are many of them available. There's the one that we are currently using is the VEX RISC-V, which is a generated core that is configurable, and it is generated. I'm trying to think what the. It's basically Scala that you use as a language, but in LiteX it is a generated Verilog blob that is being dropped into the design, and you can choose which variant of that VHDL generated core you are using by changing those parameters. By default, we use the light version and without the additional debug functionality, because the debug functionality takes up additional space. But you can add it if you want to debug your microcontroller. So the cool thing about this is this core can actually be debugged with GDB. But to do this, you have to add the debug functionality, which allows you to actually stop the CPU and interact with it. Okay, let me, this is a little bit too intense here. Let's go. All right. So then this is one of the major things we changed from FOMU. In FOMU, LiteX was expecting that there's a BIOS, and the BIOS is necessary for FPGAs that have like DDR3 memory or DDR memory, which needs training. So the BIOS itself will train the RAM interface and set it up. With the ICE40 or the Icebreaker, we don't really need it unless we go to, for example, using HyperRAM, which needs a little bit of training. But to save space, because this would be a ROM that has to be loaded into the FPGA, and we would be using pre-initialized BRAM for it. So we upstreamed, we worked together with Enjoy Digital, and we made a change. So he actually made a change so that you can disable the BIOS and directly jump to a certain address inside the flash. Because again, the other CPUs expect that everything is in RAM and not running from flash, like a microcontroller would be. They expect it behaving like a computer CPU, which loads maybe from an SD card or a hard disk, the programs, and running it in RAM. So this is a big change we made. Then this is an interesting thing. Debug, this is something Sean Cross implemented, is so-called Wishbone tool or Wishbone utils. So the CPU itself is attached to peripherals using Wishbone bus, and Sean implemented a peripheral that attaches to the Wishbone bus and allows you over serial or over USB, depending on which chip you have, to manipulate that Wishbone bus directly without the CPU involvement, which allows you to poke addresses and whatnot. So we will play with that. I will show you how that works. It's really cool functionality, actually. But if you don't want debug, then you don't want the Wishbone, what is it called? Wishbone bridge, which is here later. So then we instantiate the normal SoC core with all the standard parameters, and then we instantiate the clock generator. So the CPU and the peripherals have to be clocked. So we need to have this clock resource generator. And this thing essentially takes the incoming 12 megahertz clock, and at least the minimum what you need is generate a reset signal, so that when we start up, we make a little bit of a delay, reset the CPU, and then start going. So that would be the minimum. Then we can feed the SoC directly from 12 megahertz. And that would be the case if the system clock frequency that we can request from the command line, there's a default also set, is set to also 12 megahertz. But we can request a higher speed. Then it automatically instantiates a PLL, and we'll try to match the requested frequency as closely as possible. The default in the example is 21 megahertz, which can exactly be matched by the PLL, and it will instantiate the PLL and generate it. This is showing you the incredible power of like having scripts that generate this kind of stuff, because you can have an algorithm that is figuring out the right parameters for the PLL for you automatically, setting it up, instantiating it when necessary or when not. And so you can make a very flexible machinery using just Python scripting. It makes it very, very nice. In our system currently, we use only one clock domain. This is another strength of MyGAN. It is meant to make it easy for you to create several clock domains. And then the domain crossings, it tries to simplify this by knowing where the domains are and then doing the necessary stuff so that the signals that cross from one domain to another have the right latches and are being done correctly. So it does simplify it compared to Verilog to do clock domain crossings. So, but currently we only have one clock domain, and this is CD sys clock. So this is the system clock domain, and the power on reset clock domain is essentially the same one. It's also running at the same speed, and so we generate also the power on reset, and the power on reset is then combined with the async reset synchronizer and resets the system. So we just have a delay, and that's that. Yes, but you can just, so Sylvain is asking where I saw the automatic cross-domain crossing. I don't think it does it, you're right, I don't think it does it automatically, but because you have objects that are separate, you have an object that has a clock domain in it internally, you can just pass it to another object, and it will know automatically that these are two separate clock domains, and then do the right thing. So it allows you much more flexibility just from the programming standpoint, where you can inspect the objects that you are being passed and know what is the clock on one end and on the other, and actually do operations so that you generate the right logic for it. That's all I was trying to say with that, because each like block of logic that you're creating is carrying way more information with it than I think you can expect from a Verilog module, which you would have. Probably there is some system Verilog stuff that allows you to do similar things, but I don't know. This is pretty clear to me how I would approach it and be able to actually extract information about the blocks that I'm being given if I want to make a FIFO, for example. So yeah, this mechanism of having Python objects also, it allows you to traverse the complete object tree, and this is how you generate the documentation also. It's like you can traverse the complete tree and say, it's like, oh, I have this type of object here, this type of object here, so I can generate the documentation directly out of that, which is very nice in the realm of having to document what you're building. And so it can also tell you, it's like, oh, this is this object that I found here. Automatically, I can tell you what clock domain it is, and then look up what clock that clock domain has, because you can set up constraints for that clock domain. So this is pretty nice, I feel. All right, so now that we have the clock resource generator attached to as a submodule to us or our SOC, we can instantiate additional logic. So we have up 5K SPRAM that is being instantiated. We take 128 kilobytes of memory that we provide and then we register the memory. So this is pretty easy. You say it's like, oh, I want 128 kilobytes of RAM, and we can essentially choose what type of memory we want. So in this case, we want the ICE40 up 5K memory. So give me that and drop it in there and attach it to a certain address in the SoC. So that's pretty nice. Then we also need flash that we are running out of. So in this case, so this is something that I need to explain. The FPGA itself, the bitstream, is being configured out of this flash chip. This is a QSPI DDR flash chip, and it is much bigger than it is necessary for just the bitstream. So what you can do is, what happens when the FPGA starts up or powers on, the first thing it does, it uses its SPI interface to read out its bitstream and configure itself, and it stores it locally. So FPGAs are volatile. They are essentially like a RAM chip, and so it needs to load the configuration from somewhere. There are some FPGAs that have built-in flash, like for example the Lattice Mac XO chips, for example, have some built-in flash, or the ICE40 has non-volatile memory, which is one-time programmable, so OTP, which it can also pull out the configuration out of. Then you only need this one chip, but you cannot change the configuration afterwards. So we have this external flash, we read out the configuration, but we can, after that, still use the SPI bus for something else, like talking to the PC over USB, or we can read out of the flash and write to the flash if we want to. So we put the program, the C, Rust, or MicroPython, or whatever, into the flash chip after the bitstream. So what we do here is instantiate a SPI flash, which is this here, and we use from the platform the SPI flash for 4X. This is requesting the pins. So we are asking the machinery, give me the pins for the SPI QSPI interface. Give me those, and you pass it to the SPI flash module, and then it will already know what to do with it. It's like it will attach it correctly and do everything it needs. And you can also select what the NDNS should be. In this case, we want NDNS to be little. And we add it to the submodule. So this is how you add modules. You add submodules to, so you have your overarching design, and you attach submodules that then you can wire together. So we attach the SPI flash here, and we register it in memory and say this is called SPI flash. It is in the memory map, so this is how we can affix it to a specific address. I think I have an answer for Sylvain because I saw it here later. Anyway, so then we have we provided a bus, a SPI flash bus, and so to say we have this memory. We want to tell the subsystem that is taking care of memory management, here, have this hardware, and this is its bus, so the Wishbone bus, and here you have it, and now you can attach the memory to that bus, so it does it in the background. And then we can tell how big it is, so that's the size. And then we also, besides the memory area that we can write to and this or read from, that's the flash, we also have some config and setup and config registers, and we also register them by saying here are some config registers and this is the SPI flash. and so on. So this is then we also have the we have an additional memory region, which is the ROM, and this is a separate thing. So one thing is the memory that is physically attached to the CPU, and then the other, which we set up here, is to take, so that when it generates the C code and tells, oh, please put in the linker script this memory area and like expose it to the C code. So this is how you do it. You add memory region and say this is called ROM, and where in the memory is it? So you get it from this area. So you don't need to do it if you don't need to offset anything. So in our case, the full flash starts at 0, and then you have bitstream there at the very beginning of the flash. And then our program area starts later in the flash. So we need to tell the linker that the usable flash memory for our program starts later than the physical one that is attached to the CPU. Anyways, so that's why we need to override the ROM and say it's like, okay, this is ROM, this is where it starts with the flash offset. So this is where the actual program starts, and we also can tell that it is cached and that it should be exposed in the linker script. Okay, that was a handful. All right, so then the next step is also to decide if we want to do some debug stuff, and then we instantiate the Wishbone bridge, and we add some VexRiskV debug area. So I thought I saw something. So I don't see if the CSRs actually have a memory offset that you can set. Yeah, there probably has to be somewhere. Anyways, I would have to read the source code to find that, because yes, Sylvain was asking about that, and I'm not sure. I'm pretty sure there's some mechanism to offset them and put them to a specific, pin them to a specific address. All right, and now the simple stuff. The last thing is, so we have some LEDs on the icebreaker, and these are the user LEDs. These are the two here on the top next to the user button. So these two we want to be able to toggle from the software. And so what we do is I instantiate a module called LEDs, and we concatenate these two pins. So we request pin user LED red and user LED green. We request those from the platform, concatenate it together into a vector, and then pass it to the LEDs module. Then we can also set the polarity. So this is something I implemented, and I will show you how I implemented it in a second. So, and here is something I added so that it is documented properly in the generated documentation. So let's look how that looks like. And after we look at this, let's generate that and put it on the FPGA so you can see how easy actually it is. So I went on to explaining how this comes together, but building it is pretty easy. And then we can also modify it and add some additional LEDs, which will be fairly simple. All right, so we have a subdirectory here. So let me close the depths here. So if you look on the left side here, there is the Icebreaker Pi, and then we have some additional RTL. So I created this module, and this module is very, very simple. So all you need is, the idea was, it's like just having some GPIO is pretty easy. So it is essentially just a class, and it uses the module. It has to be taken from Migen. Then AutoCSR, this is and Autodoc. These are two features that we use. So AutoCSR is so that the config and status registers get automatically generated out of that module. That's one. Two, we have the Autodoc. This is so that we can generate documentation for it. So the first parameter is the LED pins. So if you see here, we basically instantiate a CSR storage, then pass it the length, how many bits that register should be, and the fields that it will have. And the fields are then described using the fields from the LED name. So LED name is being taken so that we have two. Let me split this view layout 2, and then we can see both of them. So LED R and LED G, these two, are the field, which is the name of the field in the register, and then the description, which is this right side here. So this two, and this automatically generates documentation for this field. The fields are giving two this is essentially the fields are a mechanism which is you could directly use just CSR storage and have 2 bits, then and write to them and set the pins on and off using the essentially the second line, which is now this is the Migen part, which generates combinatorial logic. So plus equals some combinatorial logic. We take the LED pin equals out storage, so the content of that storage register, and we XOR it with the LED polarity to essentially make LEDs that are inverse logic. So they are like when 1 off and when 0 on, so we can flip them. So we have this 1 byte that we can use to adjust the polarity of the pins. This is the 0,3 that we have here. So at the end, we have this combinatorial logic that we generate using the CSR storage. The interesting thing is the fields is more of a convenience mechanism. What it gives you is the documentation of each bit separately, as well as ability in C as well as Rust to have fields that give you an API to access those particular bits separately. So that's all the CSR field functionality does. When I show you here in the documentation, you will see we have LED G, LED R, and these are the 2 separate fields. So the fields don't have to be 1 bit wide. They can be wider or whatever. So that's how this block comes together. And after that is done, instantiated, we add the CSRs, and this is LED. So essentially, we have to still tell the machine what the name of the CSR set is, and the name was set here. So this is the submodule. So essentially, I tell add CSR from the module LEDs. So this string has to be the same one as the name of the class here. All right. Phew. This is all you need to generate an SOC. We can keep adding additional submodules here and add additional functionality to our SOC. All right, so let me take a short break to see what I missed in the chat. All right, so welcome, that Sparrow. So this is what I was worrying about. So what we are talking at the moment about, so I probably should just take a piece of paper and tell you in a diagram here. Let's see if that works. I'm not sure this will be readable. Well, let's give it a try. Let me hide the microscope here for a little bit. All right, so what we are doing is we have, and let me think, what is the best thing? So we have the PC. This runs, this is not good. This is really not visible like this. Let's see, maybe like this. So the PC, and this is where LiteX is running. LiteX generates an SOC. This SOC results in a bin file that is then, so this is the icebreaker. So the icebreaker FPGA has the FPGA itself, on top of that FPGA, we run the SOC. And that SOC is basically this bin file being put onto the FPGA. We then have a separate also compiler also on the PC. Let me make it bigger here. And we have C or Rust, for example, and this generates an ELF file or a program, ELF bin, which is then being run as a program on the SoC. And this is being run on the SoC. So this is also compiling, cross-compiling on the computer from C and Rust to a RISC-V CPU. And so you have LiteX that is generated in an SoC with the peripherals that synthesizes to a bin file, which is then loaded onto the FPGA and becomes a RISC-V microcontroller. That RISC-V microcontroller then can run a program that is written in C or Rust and compiled, cross-compiled to RISC-V and loaded onto the icebreaker into the flash. So both this and this, like virtual configurations, are both inside the flash that is on the icebreaker. The interesting thing about the SoC, it is being loaded into the volatile memory of the FPGA, and after it is loaded, we can run the program directly from the flash. I hope that makes more sense. Yeah, I know I need something better for drawing. It's like I am aware that the drawing situation is not ideal. It's better than having nothing, to at least have a diagram, but I will definitely improve my drawing game in the future. So don't worry about it. Thank you for your input. Yeah. So besides that, also, because this is why it is so complicated. So going further than that, LiteX not only generates a bin file, but also generates files necessary for C and Rust, so that you know where the registers and the memory is inside the SOC. So you generate configuration files like the linker script, which tells you where memory is, and headers with register locations so that you know where the CSRs are, so config and status registers, which you can set and reset and read out and write to do different things with the peripherals. So this LiteX generates the bin file for the SOC as well as this config files. And as another thing that it does, it generates documentation for the same thing. So this machine you configure in Python, you write it all in Python. This Python script is running and gluing everything together and generating all these artifacts that you can use them. Yes, so Sylvain, since Sylvain, you are really hitting it on the head. It really takes a lot of like getting familiar with and like chewing through mentally through all this functionality, and even using it and adding stuff to it yourself before you start like understanding how many layers there are. This even before doing FPGA stuff where the hardware itself becomes soft. So hardware is not hard anymore, it's soft too, you can be configured. Even then it is becoming a very complicated thing. So where do I compile things and cross-compile a binary that runs on a microcontroller, right? It's already a concept that is becoming difficult to understand and visualize where things are and where the blocks are, what am I affecting, what am I writing, and where it runs after that. So yeah, I hope this explanation here is a little bit visualizing how it works, and we can improve on that. Let's see, can I adjust the exposure here somehow? No, I don't think so. It's a bit dark on this paper. Anyways, okie dokes. Next, so where were we? So Jimmy has a good question. If LiteX allows emulation without real hardware too. Yes and no. So yes, it has functionality and features that allow you to generate simulation with it. I have not tried it out, and I am pretty sure it requires additional configuration. So I know that LiteX has some functionality to do simulation. I know that if you run a microcontroller, you can replace the RISC-V core with an emulator, and then run the peripherals on it. So yeah, there is some machinery that allows that too. I have not played with it yet, so I can't speak to that very clearly. Renode.io, yes, I think that's it. Yeah, Renode is a separate project, but Meigen itself, which we are using here to create the HDL, has simulation, at least using certain tools like iVerilog to simulate the modules itself. So you can simulate fairly easy, and I did that in the past. If you look on the Icebreaker Meigen example repository, some of the examples there have simulation paths, and we can play with that in the future to show how to not only synthesize stuff but also simulate stuff, because to be honest, this is something that we keep forgetting when we are trying to teach people. We usually try to teach people to go directly to the FPGA so that it's more exciting and you can actually see something work. Usually when you're designing something, you spend way more time in simulation than you do on hardware. So you simulate to get all the kinks out, and then put it on FPGA. Unless you are Sylvain, who does everything right in the first place, and only simulates to debug stuff. do I get it right, Sylvain? All right. So I think the next thing would be to essentially build this. Oh, so I should also show you what. Okay, good. So yeah, I'm just joking. I know. So basically, simulation is paradigm first. So then, with simulation, you have then insight at what each signal is doing, what the timing of each signal is, that you get everything right. And when you get that right, then you can start synthesizing stuff to the hardware and validating that what you simulated actually works on real hardware. So yeah. All right, let's see. Hey, welcome to 86 Tech. Yes, you can set synthesis constraints from inside. Yeah. I have not spent enough time playing with it. I know that the simulation in nMeigen is improved. There were several improvements over Meigen, and I don't know the details. You have to ask people that are much more knowledgeable, like Whitecork, for example. But maybe don't ask her, ask in the channel. Someone will help you, hopefully. Yeah, I need to play with simulation way more in Meigen and nMeigen to get a better feel of what is possible and what not. But yeah, you definitely, what you can even do in nMeigen, which Robert Brauch, he did in his series, which also I should probably give a shout out to. Let's see. Let's find Robert. Is that his channel? Let's see. I'm not exactly sure. This is his. So definitely, if you are interested in Meigen and simulation, look at his series about the 6800 CPU implementation. This is quite a long series where he goes into the implementation, and he also describes how to not only simulate but also formally verify. So create formal verification constraints for your design. So it is going beyond just simulation. So you actually are creating proofs how things are done right. I don't know if he finished. Okay, cool. Yeah, so I was not sure. I didn't have enough time to finish watching his series. This is something on my to-do list, but it's quite a long series, as you can see, and I didn't have time yet to just sit down and watch it all and learn more about nMeigen myself. But this is definitely something several people were recommending, and I recommend you to do that. And now that 286 Tech says spinal HDL, this is what Vex RISC-V is written in. I think it's spinal, and this is what the artifact generated from spinal. So this is why it's becoming even more complicated, all this. So if you want to modify the SoC that we are using, you don't only need LiteX, but you also need spinal HDL. And you need to generate Verilog used by LiteX for the core using spinal HDL. So, yay, onion. So we have a lot of machines generating other machines and configurations that are used by another machine that then is programmed to your CPU. So, yeah. Anyways. But for now, this is not relevant. We have one configuration that is already in here. You can ignore that for now. What we will do now is let's try this out. So as you see, we have the SOC here. So the icebreaker is here. There's a README in this directory. And all you need to do is run icebreaker py. The debug is not really necessary. This is if you want to use the Wishbone util, and then you can flash it to the icebreaker. So let me pull this out. I can zoom in onto the icebreaker like this. And maybe focus. I will have to adjust the exposure at some point. All right. Icebreaker. So this is what runs here. So LiteX, and it will tell you a bunch of information about the SoC that you're building. So it says what FPGA you're running on. It tells you what system clock you are using, so 21 megahertz. And then it generates a bunch of bus handlers, CSRs, and IRQs. So we have actually IRQs here, which is an inheritance in a certain way from the FOMU. FOMU being the project from Mithro or Tim Ansel, the tiny USB port FPGA. They use the IRQ for the USB interface. Then we have a Wishbone bus with 4 gigabytes of address space. So we are using a 32-bit Wishbone bus because the RISC-V is also 32-bit. So writing to 32-bit registers is easier with one instruction instead of multiple. So the default is actually 8-bit in LiteX. So 8-bit addresses, 8-bit registers. But because we are using a 32-bit microcontroller, essentially, we use the 32-bit Wishbone. It's difficult to say what is the... It has a little bit of a disadvantage because it does use a little bit more routing resources and more LUTs, but the speed increase is probably worth it. So we need to do some benchmarking for that. Anyways, so this is running, and this is running Yosys and doing the placement and routing of the SoC. And when that is done, let me check one thing. Okay. So that takes about 2 minutes, at least on my computer. I don't know how much longer it takes because I am also streaming, and this laptop is not the fastest. But it is definitely faster than it was because I upgraded the hard drive of it. Now it is actually at SSD, so that was a huge speed bump. Yeah. So the place and router stuff relies on single core speed. Place and route algorithms are really difficult to parallelize. I know Dave is working on some things to improve that situation and use algorithms that can be at least partially parallelized. So we will get some speed increases in the future from having multi-core CPUs. But at the moment, if you are looking for a machine that is as fast as possible for synthesizing FPGA stuff, you should look at single core performance. Okay, come on. There we go. And we are programming it. So now we there we go. So you saw the blue LED come on. This is the configuration LED. Lava Soup, welcome and thank you. So the blue LED shows that the FPGA is configured. So the FPGA will indicate that it has a valid configuration, or at least it thinks it has something valid in it if this LED is on the icebreaker. So we have a configuration, but nothing really runs yet. So what we need to do next is flash a program onto the FPGA, onto the flash chip, so that the SoC inside the, so maybe if I can, let's do this. Man, I need to fix the darkness here. Just give me a second here. Will that help? ISO, maybe ISO. Is that helping? I don't think it is helping. It's all stuck. Let's see. Come on, come on, come on. Exit. Maybe, oh, plus minus. Where is the plus minus on this camera? There has to be some, there we go. There we go. Much better. Okay, this should be better. Is that better visible? Is it too bright now? There we go. Perfect. Okay. All right. So let's focus on here. Oh, it's too close. All right. There we go. Okay. That helps. All right. So this is the FTDI chip to program the flash and communicate with the FPGA. This is the FPGA. This is the flash. And this is the blue LED. So the flash, we wrote a configuration for the FPGA. The FPGA loaded that configuration and said, I'm good. So fun fact, always use a blue LED, because if the voltage drop is too high, the circuit that we have here on the icebreaker will not work. Anyways, side note. So now we need to write behind the configuration for the FPGA our program that will run on the SoC on here. Okay, so that, I hope that makes sense. Let's do this. That's much better. And now we see something. So we have two examples in here. We have a C example, which we will start with, and then move on to Rust. So I didn't clean it up. So this creates the bin file, and let us look at the C program. C program is here, source. Very, very simple. All it does, it writes an A to the RxTX register. So UART RxTX write A, and then writes to the LED register a value that is stored in X, which is 0, and it can toggle essentially back and forth. So it is toggling between the red and green LEDs, and then sleeps for 80 milliseconds. And that mSleep is implemented in the timer, which uses a hardware timer that is also a peripheral that is pulled in into the SoC. And so to show you where so there are include files for and these are generated, the CSRs. There you go. So let's do the RxTX. So see, this is what lets out read and lets out write, and these are the addresses in here. So this is very simple to basically, and this is generated from LiteX, so you don't really have to figure out what is. Sylvain asks if the RISC-V software is running directly from Flash. Yes, it is running directly from Flash. The Flash has a cache, so it is cached execution, but it runs directly from Flash. We don't have enough RAM memory. Well, we have for very small programs. We would be able to move the program into the BRAM local FPGA RAM and then execute from RAM. But because we want to be able to run bigger programs, we run directly from Flash. So yeah, that's a good question though. And this was part of the BIOS being able to use Flash as our execution start point was a little bit of a problem which we fixed in LiteX. Now it is upstream and now we can do these things pretty easily. So yeah. So in CSR and then in main, all we do is write and write the other one and then the LEDs. So essentially what you see here, the LEDs should toggle. And when we connect over serial, which we can use the FTDI chip to connect over serial to the FPGA, in that serial console, we should see an A being printed all the time. So let me open a new terminal. And let's see. USB 1 and then 115200, I think. Oh, I don't have screen installed here. Okay. Serial port setup, A, USB 1, and then no flow control, yes, and then exit. So now let's do make. This will build the program, the C program, and then make Flash will write it to the Flash here. Oh, what? Make prog? Make prog, sorry. So now, let's see. The other way around. There you go. Now the LEDs are blinking. Now let's see if the terminal shows something. There we go. Yeah, a lot of A's. There we go, perfect. So, control, oh God, A clear? Yeah, there we go. So it is writing A's. So yay, woo! Yeah, we have 128 kilobytes of RAM. That is true. It is fairly big amount of RAM, but the thought was that eventually we will put MicroPython or CircuitPython on the Icebreaker. So that's why I wanted to make sure that we have enough space so that we can put the glut of Python onto the microcontroller here also. So yeah, that was the reasoning behind it. It's screaming into the void. Yeah. Yeah. That's exactly right. It is trying to communicate, at least. Isn't that right? It has character. Yeah, it's a different Hello World. Okay, so yeah, now we have this working. So now let's do the same thing, and I will wipe the FPGA once again to make sure that we are programming with Rust. So the second example is the Rust example, which we have here. So Rust is a little bit more complicated in the sense of how the environment is built. The reason is, well, C is really shallow layer. It's very simple. You directly access the addresses. With Rust, you want some more safety, I guess, and it also has multiple crates that you have to pull in. So for an embedded Rust target, you not only this Rust target, let's see, we have the source here. The code does exactly the same thing as the C code. So this is Rust. This is we mark it as an entry, is the main function here. And we take the peripherals from this IceCube Icebreaker example SoC, IceBSoC pack. And this pack is here. We have this pack here on the left, which contains some special code. So this pack automatically takes the SVD file and generates the headers. So when it is being compiled, it runs this build.rs, which generates the headers, the necessary code for you out of the SVD file. So it automatically updates as soon as you synthesize a new SoC. So SoC in LiteX generates the bit stream, automatically also generates the SVD file. And then if you go to your Rust project, it automatically sees the SVD file changed, generates new access code for that, and provides it to your compiled software. In the C example, there is not as much automatism. You have to copy it out of the SoC project. Anyways, I probably should write this up a little bit more in the readmes, but it is pretty obvious as soon as you start playing with this. All right, so this is the IceBSoC pack. This pack also relies on the real-time wait, not in here, main RS, there. So this is your access to the hardware. So this is the CSRs and memory mapping. And the rest is RISC-V runtime. So RISC-V runtime is a upstream official crate that provides the necessary setup infrastructure to write programs for RISC-V targets. We had so this is also very recent. It was part of this whole effort, is to get the necessary functionality, and someone was already working on that, and it's a huge thank you to them that they merged the changes that were in FOMU runtime crate necessary to run on a RISC-V that doesn't have floating point support, that they added the RISC-V32 IM functionality so that we can use the official RISC-V runtime for this SoC that we have here. So that is nice that we can just use the upstream Rust crate for this. So IceBSoC is being generated on the fly. This is something that will probably stay as part of your project. If you have a microcontroller, you can just publish it and make other people have access to it and use it. If you have an SoC that will be changing on the fly while you are adding additional hardware and you are tweaking it, adding some peripherals, removing it, changing features, adding bits and whatnot, you want this crate to be auto-generated. So it will be part of your project probably, or at least a separate repository that you have sitting somewhere that you will automatically update out of your LiteX generator. So that's why this crate is part of our example repository. Okay. So this again, so what I did here is actually do some Rust shenanigans to force with unsafe code to actually override the print function so that we can just use print macro to write A's just normally. So this is something derived from the really awesome project. So this is the moment where I should give a shout out to 222. Where is it? Betrusted. So you might have heard of Betrusted, which is a project by Bunny and Sean Cross and a few others. So they are trying to make a secure enclave, open source. It is essentially what we are doing here. On a bigger FPGA, a dedicated RISC-V SoC, a real-time OS that Sean is writing in Rust, as well as the applications written in Rust. And so this is I was borrowing a lot of stuff, and Sean was basically ripping out parts or like showing me parts of Betrusted as examples and throwing them at me. And this is a bunch of the functionality here, especially the Rust part, is derived from the Betrusted repository. So if you are interested in some examples in here, so there's a repository. Oh wait, there. GitHub Betrusted.io, I think. No, Betrusted. Is that what the org is called? Yeah, there we go. So if you look here, this is the org, and there's the Zeus kernel, and then there's a Betrusted SoC. So this would be the LiteX part, the Betrusted SoC. Then Zeus kernel is the Rust code, and then we have Zeus core. This is like a BIOS startup core. So this runs first, and the kernel runs on top of it. And then we have a huge repository with tons and tons of gateware. That is very useful. Sean was showing me a bunch of stuff in here. One thing that will be very useful is a tick timer, for example. So there is a peripheral. This tick timer, unlike the timer that we currently use in the example timer runs at the SoC clock speed. So it's very fast. So you can measure very fine things, but it is very fast. Usually in a microcontroller, you want something that runs at the CPU tick time or the OS tick time. So this is the tick timer, allows you to add a divider so that you are not running at the full CPU clock speed, and the timer can last for a longer time. So this is one example that is useful. And we will be using it in Twang, I think, when we start porting the game to this SoC. And another thing that Sean showed me in here, which is very useful, is there is a random number generator somewhere. My blind CPU timing ASRNG LiteX. Is that it? I'm not sure. No, this is AAS. There is a ring oscillator timer, essentially. Oh, welcome, Sora Division. Thank you for joining. Anyways, I am blind. It is somewhere in here too. True random number generator, TRNG oscillator. There we go. So this is a ring oscillator, essentially. that you can use as a random number generator. So that's also useful. We will need a random number source. Well, we could actually use a pseudo random number just calculation, but we could also use this from the good guys from Betrusted. All right, so now that we have the Rust code here, this example, and we went on the tangent to talk about existing places to use stuff from. Essentially, what we do here is take the peripherals. So this is a singleton to get the peripherals so that they are used only once. Then we send it, we give the UART to our print hardware so that we can use the print macro. The timer is we generate a new timer and give it the timer peripheral. And then we have LEDs, and this is the LED struct and its implementation, where we can set, create a new, and then set and off and on and toggle and have all the operations on the LEDs. And that is, we give it the hardware itself. So this is how you would write a driver. You have a struct that you give the hardware registers to, and then you can essentially just set the bits in this case for the LEDs. So we can also toggle the LEDs. So all it will do is set the LEDs one to on, one to off, or one to off, one to on, and then toggle them while it is printing, just like we had in the C example. So let's just run this. And in Rust, we just do cargo run and then release. And this will build the pack, as you see. It is building the ISBsock pack, then the Blink example, and it is flashing it. And now we have it running already. Perfect, all done. So this is essentially what we have in the example repository so far. That took a little bit of a while to explain it all and go through all the sections of it. So I will take a very short break, be right back. And if you have any questions that I can answer now, I will be happy to answer this after I come back. Also, I think what I would like to add is add control for the head so that we have some buttons and maybe some LED control. We don't have much time left, but I will try to at least add some additional LEDs that we can control from our Rust code. I think I will just go directly to Rust to simplify things. All right, be right back. All right, I'm back. So, what were you folks up to while I was gone? Sorry, division. Yeah, Rust to simplify things. So why I'm saying to simplify things is because using Rust, it auto-generates things faster. It's like I don't have to copy stuff around. C is simpler in a different way. It's like I feel in Rust you put more upfront effort for less effort later. That's how I feel so far about Rust and how to use it. So this is why I think it is simplifying things for the future you. Especially because you build a little bit more infrastructure beforehand, like having those drivers to access the peripherals, and not just directly manipulating bits. It's like, yeah, it is easier to just poke around in the registers with bits, but if you have that infrastructure, you can move forward faster later. So yeah, it's a trade-off thing, and so far I enjoyed writing Rust quite a lot. It's another skill that I learned this year. It's like I used a little bit Rust in the past, but I actually learned it only very recently. I put the effort in actually learning how to write it, and it is a steep learning curve. But when you get through that and start like understanding how it thinks, it's becoming more and more fun to actually write. And especially you see it's like, oh, I'm doing these things so that my future me is feeling better and not as frustrated. So yeah, it's a thing. I almost finished a USB device part already. Works good, but utilizes 99%. So you implemented a USB device for the ICE40, or what did you build? Yeah, these things can grow quite quickly. There's several implementations by now. I think Savin has an implementation, and there is one in FOMU. So there are different approaches to the USB stack. So, Jimmy, I'd be interested in seeing more on how a cross-compiled app gets loaded. It's been having some problems when LiteX term. Well, so in your case, so Jimmy is running it. This is another project I should give a shout out to. So Jimmy is part of the helping the Radiona group with a project called ULX. Right, let's see. Radiona. So this is an FPGA development board that has an ECP5 FPGA on it. It's a much bigger FPGA than the ICE40 on the Icebreaker. Oh, I should show you the screen, shouldn't I? There we go. That's better. Oh, Valente USB and Rust. I see. Yeah, so that's very cool. There is a USB implementation for FOMU, I think, for Rust. I'm not sure. Is it the same thing? Maybe it's the same thing. And then you should definitely look at the Betrusted stuff. They might also have already some USB implementation there, because it also has a USB stack, but it's not, I think, Valent USB based. But yeah, this is definitely useful. Jump into our Discord and tell us about your USB implementation, because that's definitely interesting. So yeah. So yeah, back to Jimmy. So Jimmy and the Radiona folks, they are working on ULX 3S, which is an ECP5 board. It is now funding on crowd supply, so definitely get one of those for yourself to play with. It's a quite powerful board. It has a lot of peripherals. It has SD card. It has Wi-Fi interface. It has audio, HDMI, and whatnot, and a bunch of PMOD interfaces. So these connectors on the side are actually PMODs. So the fun thing they did is actually they have two PMODs, and between where the pins wouldn't be on a normal PMOD. So here, the pins between. Wait, can I show you this? It's really dark again. There we go. There we go. So yeah, see there's here we have the auxiliary power, and they use that as pins, additional pins too. So you can actually plug in a dual PMOD in this side as well as on the other side. So this is a neat trick. And so yeah, check out that project. So Jimmy is asking, he's curious about loading applications using LiteX. The tricky thing here is, on an ECP5, you actually would run a full BIOS on it, which on the ICE40 or the Icebreaker, we are not running BIOS on it, so there's not a LiteX bootloader in here. So we are not using the LiteX term to load the application onto the FPGA. What we are doing instead is, if we let me show you. Let's see, what is the best spot? So this is the Flash script. All it does, it takes the binary, the output binary from Rust in this case, it object copies it into a bin file, and then uses iceproc to put it at a certain address in the Flash. That's all it is. In the SoC, so we put it in the Flash at offset 40,000. This is where the binary that will run on the RISC-V core end up at. And we are setting the jump address for our application in here. Let's see, where is it? I think I set it, the offset, it's the offset. There is the offset. So you can give it as a parameter to the LiteX SOC generator. So Flash offset default is 40,000 in hex. And we pass it to the SoC, and the SoC takes that offset and passes it on to the CPU reset address. So our CPU reset address is not the BIOS, which is the normal behavior for bigger FPGAs like the ECP5, where the BIOS would be. Our application is directly being jumped to. So we don't have the BIOS, we just directly jump to our application. And we can set the address where it should jump to. I hope that answers your question. Okay, let's see. Let me try to keep up with the chat a little bit more. Speed device resets automatically. Yeah, so that's the difference, Sora Division. It's like on a small FPGA, you don't need that. With the BIOS and bootloader, you need to have a little bit more complicated thing. Okay. So speaking of problems, when I flash the firmware and replug the board, the firmware works for a fraction of a second and then hangs, and is sort of a known problem. running what exam? Blinky. Okay, so the Blinky. Oh, the project on stream. So yeah, let me show you when it does that. So let me quickly. So Zero Division is asking if it is a known problem that when you run Blinky, it stops after a fraction of a time. So the reason for that is in the Rust example specifically, because I don't think it does that in the C example. Let me just show you when I do the following and I enable debug. This is what will cause it to log. So the reason for that is when we enable debug, the serial console that we are writing to is not just the UART. It is actually a special loopback UART-like device that is part of the Wishbone tool from Sean. So Wishbone Bridge, if we look here, is instantiated here. UART Wishbone Bridge. And this takes the serial interface and makes the physical serial interface a Wishbone tool interface. You want me to just replug it and yeah, it runs. It shouldn't stop. At least not when it is not in debug mode. In debug mode, it has a buffer. Essentially, it runs the buffer full and then it will stop. So that's the explanation for when it should stop. Otherwise, it shouldn't stop with the debug interface. So this is synthesizing with debug. Oh yeah, so let me show you the debug functionality, because before we start adding other functionality, we should probably finalize showing all the features that we currently have. So after this synthesizes, we can use the Wishbone tool to actually poke around with things. So running simulating annealer placement, refinement, we can close this. Leave Minicom, yes, we don't need Minicom. Replugging breaks something. Yeah, I don't know. That's a good question. It shouldn't do that. In theory, it should keep running like this as long as there is a serial port to accept the data. So our Rust code here in printrs, this is actually checking if the TX is full. And this is only correctly rigged up. So we don't have the CTS, RTS pins connected on the FTDI chip to the FPGA. So this is why when it is a physical interface, it just keeps writing data. But for when we have the debug interface, it actually has a buffer and it has those virtual pins connected, so it will run the memory full. LiteX serial. So write, yeah. So this would be the alternative of writing. Yes. So so this is possible. This was an alternative approach that I was looking at. It's just using read-write for serial interface. That's an alternative way of implementing them. Tom, welcome. Thank you for joining. Yeah. So is it now finished? It's almost finished. It's still doing its thing. Yeah, it is a bit bigger. So people were also asking, Holzfrau, thank you for subscribing. I don't, the term is not subscribing, right? It's following the channel. Yeah, following the channel. Yeah. So the debug stuff does take up much more space. So let me look. So see, the FPGA is like 87% full if we enable debug. If we don't have debug enabled, let's see if I can find the non-debug version. It's 77% full. So we have a bunch of stuff in there. I think I could make it even smaller. So there are multiple ways of making it even smaller. It's like there's also a smaller Vex RISC-V core that can be used. We could eventually also switch to the, yeah, see, this is, let me finish the previous sentence. We can switch to the RISC-V or Pico RISC, Pico RV core, Pico RV. The problem there is the trap, the implementation of trap instruction is not the standard one because Pico RV was implemented before that was standardized in RISC-V. So, and no one came around to actually update it to the standard way of doing this, and Vex RISC-V has that functionality by now. So if you're using the trap or enabling, disabling interrupts or traps, then your code will crash on the Pico RV. So you have to remove those instructions if you want to use it. So, There, for Pico RV, oh, that's good. Yeah, I probably will take a look on the Pico RV. So Pico RV has certain advantages. It is also a little bit fast, or it's designed so that it can be clocked faster, even though it uses slightly more clocks per cycle, per instruction. So there's a little bit of a trade-off, but there are very good reasons to do that, especially if you have a USB core, because you can run it at 24 megahertz. Anyways, watch TNT's or Sylvain's streams. He explains that very well on his Twitch. So definitely, Sylvain, drop in the link to your Twitch channel. There he makes very good points in there. So now that we flashed it, now you see it locked. So if I repower this, it is blinking for a little bit and stopping. It's because the buffer ran full. So Wishbone tool, this is the tool from Sean Cross. Let me see. GitHub, and it is Litex Hub. Wishbone utils. So this is where you can find it. Wishbone utils. You have to clone this repository and then install it with cargo. So cargo install -- path. Yeah, so like this. So this is how you would install with cargo install path dot. You would install the Wishbone utilities onto your computer so it is in the path. Now, Wishbone tool. So first thing you can do, now that our CPU is locked, so this is the address, if you see here. Let me maybe make it even bigger. So, Wishbone tool. Interface is the UART, and this is the address where the LED status register is. And we read it out, and the bit 2 is set, which is the green LED. What we can do now is set it to 0, then the green LED should go out. The green LED is out. And we set it to 1, the red LED is on. So now we can poke directly in the memory of our SoC from the Wishbone tool, which is really cool, I think. And then 3, you can just have both on. So we can poke around with the Wishbone tool. And now we can also have a terminal. So this is the originally physical UART that we were writing to but fed through the Wishbone tool in the debug mode. And now our CPU is still running and doing the toggling, and we see the A's come out on the terminal through the Wishbone tool. It's not as fast, but it's there. We can access it. So that's very cool. And the third thing you can do is run GDB. So this is starting a GDB server, just like OpenOCD, for example. And we can now go So I'm taking a RISC-V GDB and then running it on the Rust RISC-V Blink application. And then colon 333. And there we are. And we have GDB for our Rust program on the Icebreaker through the Wishbone tool. So we can debug our code. Isn't that cool? I find this so cool. It's such an onion of mechanisms plugging together that you can do stuff on a microcontroller, and then you can, when you don't need it, you can remove features like debugging out of your design to save space. And modify it. It's really awesome. And having tools like Wishbone tool is really amazing. And one note to that, we currently don't have breakpoints here. So just to explain the magic of this. The VEX, so how breakpoints work in GDB is if you are running an application from RAM, you can have so-called software breakpoints. This replaces an instruction inside your code in RAM for a trap so that it drops out into GDB. We can't do that on our microcontroller because it's running out of flash and we cannot modify the flash. So we need hardware breakpoints. The VEX RISC-V, even in the debug mode, does not have debug or breakpoint registers or breakpoints added to the design. So to enable those, you would have to resynthesize the VEX RISC-V using its own machinery and add some hardware breakpoints, and then add it to your design. So this is something that Greg DeVille did for the Orange Crab, which is another project that I would like to give a shout out to. So besides the ULX3S, there is another campaign going on currently, which is the Orange Crab. And this is on GroupGets, I think. Orange Crab. There we go. So that is Orange Crab. It's another ECP5 based board in the format of a feather or Adafruit feather. Yeah, Scala. You need to install Scala to synthesize the VEX RISC-V, which, yeah, it's a thing. But yeah, check out this project. It's another really awesome board. At least check it out for the photos. The photos are just delicious. Greg makes the best photos in the industry, I think. So yeah, Orange Crab, and he did that for the Orange Crab to have hardware breakpoints for his design for LiteX onto the Orange Crab. So I will take a look I will try to do the Scala installation, generate a VEX core that we can then have also in the example so that we can use that eventually. So that's one of the to-dos that will come so that we have actual hardware breakpoints on the Icebreaker FPGA 2. But yeah, but at least you can step through the code, that works. and you can see what is going on in the FPGA and inspect variables and stuff like that. So that is pretty cool. All right, so connection closed. We can close this. We don't need it that big. Compressed instruction set while there. Yeah, it's like I think we should. So essentially, if any of you have time to play around, have an icebreaker, have some time, try out the example repository. Get it to work on your CPU, give some input, open issues if you have some ideas what we should improve, add, to-dos, requests, and definitely pull requests are very much welcome. We already got a few pull requests to improve the Rust Rust stuff, and yeah, if you have some additional examples, code examples that you want to add, they are very much welcome. Yeah, and let's do that on the repository with the examples. Okay, so now, what time is it? Yeah, we are about 2 hours, but let's. I think that is all now described what you can do with this. But I still would like to add at least one little thing to the design before we wrap this up. So to do that, let's add just some more LEDs to the design. Let me think. I think this print we can close. Let's see. So all we need to do is add a few more LEDs on the head here. Let me see what this. Yeah, memory bandwidth. Yeah, so there's a bunch of things regarding speeding up this design. So we are currently using the system clock to do the QSPI interface. This could be running at probably at twice the speed than it is now. So we could have a separate clock domain and run the flash interface at double the speed of the CPU. This is something the PLL can do, is provide a half-speed clock, so we can run it at 42 megahertz, the higher clock, and then have a half clock of 21 megahertz for the SoC. So we could theoretically have the QSPI interface running at twice the speed. Also, this QSPI could be also DDR. Currently, it is not. So that could speed up things theoretically. What else? Yeah, using a small the compressed instruction set might be a good idea. Yeah, and probably a few other things of running different peripherals at different clock speeds. Yeah, so I'm sure there are improvements we can do to speed up this little puppy. Okay, so let me open the depths. So C, depths, LiteX, boards, platforms, icebreaker. So what we need to do is platform, add I think that would be it. Let's see if I need to, if the platform is imported as such. Icebreaker platform. We need to import also break of pmod. So we added that, and then we can request some more pins here. Platform.request, and we can request user-led R, which would be the center one. So led R would be this one. So that would add an additional pin. If someone can explain, okay, so there are questions here. Using a good cache, yeah. So Sylvain is plugging his own thing, yeah. So that is why I'm telling you to follow Sylvain's streams, or he posted them also on YouTube. I really recommend that you see that he implemented a pretty nice cache for memory cache that can be used with the SoCs. The advantage of it is not just targeted at Wishbone, which is fairly slow, but also can target the CPU specific interfaces. So this will be a very nice speed improvement when we can get this also into these Litex SoCs. So yeah. Oh yeah, so Sylvain was asking, I don't really want to like go on another tangent, but yeah, if you, for example, want to add a Verilog implementation of something that you already have, so this is in course. So this is a good example of how, for example, a PicoRV is added. So PicoRV just has this Verilog directory. So this is the Verilog itself for the PicoRV32. And then you have the core, which is the Python, just a lid, just an adapter that takes the Verilog and connects it to the MyGen interface. So you have this class just like you would have for a normal module. And then it has a little bit, some setup parameters. But the interesting thing is here somewhere, init, and then it sets up the signals and then adds the sources, this is where the Verilog is being loaded. So you can add the Verilog sources, and all you need to do is show what the interface of that Verilog module is to the MyGen interface. So it is very, very simple to add, and there are even params that you can pass to the Verilog code using this these structs. So adding your existing Verilog implementations to the Litex stuff is fairly easy as far as I can tell. I have not done it yet myself, but this is all you would need to do. All right, so yeah, let's add that one LED in here and go from there. How do we call it? LED or HLED R, so for head LED. Something like that. How to write a new MyGen part. Yeah, so essentially, we can look at that in we can talk about this stuff, but essentially all you need to do to add a new module to MyGen it's essentially just a Python class. So these LEDs here, I have this from RTL LEDs import LEDs, which is my own Migen module that controls the LEDs. So that's all I import in here. Then I instantiate it and assign it to just a random my choice named variable in submodules, and then this is the implementation, just this Python module here. So then you have the CSR storage stuff, and then you have combinatorial as well as synchronous stuff implemented just like you would in Migen in general. So either Migen or you import stuff from Verilog that you might have. So yeah, I think the further we go, maybe in future streams we will be adding more complicated things and more modules. And so this will become apparent how you add new modules to your design and to your SoC. So currently I'm just modifying this one module that already exists and just adding an additional bit that is then being linked to this platform pin. So this bit inside that register that is part of this module will be assigned to this pin from the platform. I hope that helps a little bit. All right. I think I'm a little bit lost of what you guys are talking about now, because it seems like you are talking about compiler stuff now. So yeah, anyways. All right, so I added that one pin from the extension. So we should be able to save this and rebuild this core. And this one additional LED should be running. We don't need debug, so we should build this. Let's see if this explodes or not. Yeah, so I am using the compiler from the Sci5 people, Sci5 website. So that's the RISC-V compiler I am using. So you see, this is the RISC-V64 unknown ELF. So this is directly downloaded from the Sci5 website. But yeah, there are plenty of different compilations, different platforms, or different distributions of the compiler for RISC-V. This is taking a while. Oh, okay. So it is building actually. Okay, good. That was stuck for a long time. Yeah, it takes about 2 minutes, I think, to synthesize. So yeah, it does take a while. So I rather try to make a little bit more impactful changes than just adding one pin. We can start looking into here how to add more pins, because the interesting thing is also how do you access these additional pins. And I remember having a little bit of issues here. I think how it worked was user led G, and then I think the pin number, like this. Yeah, I should just copy this over. Is that 5? No, it's 4, right? All right, so this would be 1, 2, and 3. I'm sure there are more efficient ways of writing this. And then, let's see, comma. Still synthesizing, good. So this is the number 2, because they go from 1 is the red, 2. Like this. This is not great. Oh, left. So this is, I think, how... I'm not happy with this. Anyways, I will yak shape this into making it a little bit cleaner later. Oh, there we go. So, as you see, it already programmed it, and we have this additional 1 LED blinking. So that was pretty easy. So we can add this. Let's add the remaining green LEDs. Let's hope that works. Oh, welcome, Lotarmash. I think that's the name, how the name is pronounced. Welcome to the stream. Yeah, we are adding some more hardware here. So, four. Okay, so I will document it a little bit better later. 1, 2, and 3. So let's save this. This should do this. Let's see if that works. It's not complaining, at least. Oh, Sajatak, thank you for the Twitch Prime. Thank you very much. All right, so yeah, this is synthesizing. And what we can do in the meantime is update the documentation, because it already, did it generate the documentation? I think it does it later. So to update the documentation, so this is the line that I'm doing. So it's the Icebreaker Pi, document only, and then Sphinx build. So it is using Sphinx to generate the documentation. So what I need to do is activate the venv so that I have the Sphinx added. And this would rebuild it, but let's wait for this to finish, because I don't really want to disturb it while it is building the sock. And then when we do that, we should have updated documentation that has more, that has the additional bits implemented. So let's wait for that. Let's see where the documentation will land so that we can update it. Oh, so by the way, after I show you where it is, so this is the documentation locally that I have on my computer. So this should update and add additional bits here and fill this little bit in. But also, if you're interested in seeing the same documentation for the examples have the documentation is also, this is on Icebreaker FPGA GitHub IO, and then LaTeX examples. I think I linked it. No, I didn't link it. Maybe it is linked in here, in the README. No, it is not. Oh yeah, there it is. You can find the generated documentation here. So the documentation is also available online so that you can read it. This is using the GitHub IO website hosting system. So you can definitely do that for your own SOCs when you share it. The fun fact here, it's like you need an organization website first before you can create a repository specific website as a subdirectory. So that threw me off for a little bit. Okay, so where do we have this here? Still synthesizing. There we go. Almost there. Let's see. Will it blink all the way? Yeah, all the LEDs are blinking. Very good. Dun, 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 dun. Okay, so we added these additional pins. So that's how easy it was. It's like I just hooked them up. And now let's do the documentation. Oh, it still requires export SFT, export SFT. There we go. Doesn't really need it, but it requests it. It's fine. Okay, documentation regenerated. And reload. Ba-bam! And here we go. And now we have the additional bits. That's how easy it was. It like just regenerated this. And now we can go into the Rust code. So let's go here. Let's close this. And then we can go into the Blinky code. And then we have the LEDs here. And so this is what the fields are useful for. We can have LED-R, LED-G as direct accessors for the single bits. So we can add them here, or we can just on-off. This will set all the bits on-off. I see. This is just using the 3 bits here. Yeah, this should actually be a full toggle. Is toggling all the bits. Toggle mask, so it is toggling all the bits. So we can, for example, add here the head red LED. So we will invert it. And all we need to do is this, and then write bit high red. Yeah, I think that's what we need. We save this. And then where's the main? And we add here true. Let's toggle it, so true. So now it should, the red LED should be the opposite blinking pattern to the green LED. So they should toggle between each other. So that's the goal here. Let's see if that works. Let's go here. Let's see if that works, or if it will explode. I missed something? No. So yeah, the cool thing, this is what I'm saying about like Rust being simpler in this particular case. I wish I could. Yeah, there you go. So now they are in opposite direction. You see, it's like when the greens are on, the red is off. I hope this is visible on stream. Anyway, so this is how easy it is, and Rust just regenerates. If you see here, it regenerated the pack because the sock changed, and I get the new accessors just like that. So I was able to just access the bits with the names that I described inside the SOC. So if I do this here, so these are the names: LEDR, HLEDR, HLEDR. It automatically generated this. So there you go. So that's how easy it is. We can also add buttons and other things where I create a new class. But I think for now, this is all that we will do today. I went through a long explanation of what we have, how things work. I hope I was able to answer some questions, and I hope this was somewhat useful to get acquainted with how these things work. The goal for the future is to expand the examples a little bit, like add buttons, maybe add additional examples, without making this too complicated. The example stuff. And the actual goal is to use the example repository as a template, make and start a new repository for the Twang project, for the LED game project that I started earlier this year. So yeah, the joystick and the LEDs are here. And yeah, so the goal is to figure out, to make that SOC, move it over, start a new repository, and start adding specific hardware for it. So they have a pixel processing unit type of hardware for the LED string, for the LED string, and have like inputs for the joystick, maybe even have a state machine that reads out an accelerometer for the spring-loaded controller, hook that up to the microcontroller, and write the game in Rust itself and run it on the SoC. So this is just a stepping stone. It took quite a lot of effort, but I'm pretty happy with what we have now, and I hope this will be useful for people as a template and to learn how to build their own SoCs for FPGAs, and trying to keep it simple as possible. All right, so yeah, hi Scott, thank you. I'm glad it is useful, and 286 Tech, thank you. Yeah, so all that said, I think that would be it for the core stream part. I will now sign off, and thank you for watching, and have a good one. Also, I want to say thank you to the Patreons that are making this possible. So this is also an important message that I would like to convey. These streams are really only possible because of the people that keep buying the Icebreaker hardware, as well as support me through Patreon. And there are some people that are just trying to make a quick buck on the Icebreaker already. So I really appreciate if you guys, if you can afford it, buy the actual hardware from us, instead of getting it from some other sources. The official sources are CrowdSupply is a good place to buy it, and then Mouser is an official reseller, as well as the 1BitSquared store in the Germany and US. Yes, we have a German store. It seems to be still not clear that there's a European store you can buy this stuff from. So yeah, 1BitSquared DE is the German store. 1BitSquared.com is the US store. We still have the US store and the German store have some inventory. I think CrowdSupply currently is in back order, but we will be making more Icebreakers this coming week. So there will be more inventory. So I appreciate if you guys support us, as well as support the ULX people. They are doing an amazing job, as well as Greg with his Orange Crab. Yeah, so thank you very much. And the Patreons that need a shout out is Edward Brodin, Jerzy Hacker, Jordi Parky Rodriguez, Sid Price, and 2 new supporters, Tom Keddy and Kelly. Thank you, Kelly, and thank you, Tom, for supporting this. Yeah, I really appreciate this community. We make awesome things together, and let's keep doing that, and stay warm and stay safe and stay healthy in these difficult times that we currently have. Yeah, so thank you for watching, and if you have been, see you later. Bye.